Here we go. Now this is looking pretty cool. Hi, the other day I was looking one of the episodes of 8-bit show and tell channel, and where Robin explained about this 10-print orthogonal basic program, which is actually a variation of famous 10-print maze. And what was so specific about this little program is that it was a part of the competition for the smallest program in size. So this one particular was 32 bytes long. It was written in BASIC, and you can see how it looks in the bottom right corner. And there was some quirkiness about this program and what author of this program made to get so small in size. And Robin was talking about that, so this is not something that interests me very much. What I was thinking about is it possible to make this program in assembly language? Is it possible to make it 32 bytes long, or even smaller than 32 bytes, or is it not possible at all? You have to keep in mind that this basic program is very optimized. It's using some of the functions that are of course possible to do in assembly, but they take much more bytes and commands to do it, but we will try nevertheless. So just to show you the sizes of some programs. So this is the 10-print orthogonal that Robin was talking about. So it's 32 bytes long. And for example, just for comparison, this here is classical 10-print maze, and when we convert that into basic into Commodore program, it contains 30 bytes in length. Okay, and if we do a little bit of trick and transfer this to line 0 and remove it here and compile it, then we will get a program with 27 bytes long. So what we are going to try to do today is try to write orthogonal maze in assembly. So the first attempt was this. So the idea was to take a random number from the SID chip, of course, create our array of characters, and take the random number from the SID and end it with end it with 8, so 7 to take just last 3 bits of byte, and this that will be our index for this array. So because of the we cannot go below 7 here, we added additional two characters here. We are not even possible to use any kind of delays and something like that, because even this is too big. So if we try to compile this, we will get the size of 38. So it's way over 32 bytes, so there is nothing we can do about this. Maybe we can remove this, but it still would be way over 32 bytes. Let's see. Yes, 37 of course. So we cannot use the SID chip as a random number generator. So the next thing that I try to use something else. So I try to use the raster line value position and try to add some numbers and some other bit manipulation, and use the register that is screen code of character under cursor, possibly, if that makes any more randomization if possible, and the rest of the code is exactly the same. So let's try to see this. Okay, let's try to do this, and this time we are at 32 bytes, and let's try to see how that looks in twice. Okay, so 4 to 1 to 5, and here we go. Let's try to slow it down a little bit. So it's not much. I don't know how good this randomization is, but here we go. It's working. It's just simply too fast. The next thing that I tried to do is just simply remove these two additional characters here and leave the original 6 characters, and try to add comparison and just eliminate these additional 2 possible indexes that we came up with. So this just leads us back to jump back to loop if in case that we get indexes like 6 or 7. So this was also size of it was 34. So this was not going to work also, so nothing about that. I was going back and forth with this problem, how to generate a good enough random number without actually having one, and to be still under 32 bytes. So I need something fresh, so I need something to completely different. So that I found. Then I found something that is called pagetable.com, and here we have all the decoded, disassembled kernel, all the memory addresses, registers, and so on. So I found tried to find something about random generator, a basic function um, R&D. So I found something. I found its routine. I found registers, memory locations where it stores his values, and I try to use that approach. So let's see how that turned to be. So this is our first attempt. So what we have here is just one moment to switch back to here. Okay, so this was our first attempt. So this is at this memory address is basic random routine which we call, and that generates random numbers, and it stores them at this addresses from 8B to 8F. So I choose to use one of the bytes, and again end it to get from 0 to 7 indexes, and just print use again kernel routine to print out the character on the screen. So if I compile this and try to see the size of it, so we have now 28 bytes, which is great. But let's see how it's running. So let's try to do this. Here we go. This 152, right? Okay, and here it is. It's much more slower because we use routines from the kernel and basic, so but that doesn't matter. What matters is that we are now at 28 bytes, and this is looking really good, but we can still improve a little bit more. Let's try to do to remove this again, to remove this additional 2 characters and leave just original 6th, and again we will loop until we get from 0 to 5 indexes. So let's try to build this one, compile it, and see what size it is now. 29. So we are still under 32 bytes, which is great, and let's see how that program works. 152, and here we go. Is it any different? Maybe, but still looking great. But then how about this regular diagonal maze? Can we do that one? So I made this. So this is the regular one diagonal 10 print maze, written in assembly using the same technique, using the basic random function, and this time we just need last bit of the byte, so we will use 0 or 1 index, so 1 or 2nd character, And let's try to build this one. Compile it. Let's check the size. And it's 21 byte. We have 21 bytes, and let's see how that performs. So here we go. Now this is looking pretty cool. But of course what we need to do next is test all these little programs or variations on real Commodore 64.